Section 8.8 is improper integrals. Up until now, the integrals that we've been working with have had two basic requirements, that being that the domain is finite and the range is finite on the finite domain, meaning that we'd have something like a graph like this, where we wanted to find the area underneath the curve, and we would have finite points here from a to b, and we would say that the integral from a to b of f of x dx would give us the area under the curve. What we're going to be looking at in this section is where we have limits where the bounds go off to infinity. So that's going to be different, and that's why they're called improper integrals. In graph A here, we have the function y equals the natural log of x divided by x squared. And if we look at this as x goes off to infinity, because we're dividing by an x squared, the y value here is never going to be equal to 0. We have a decreasing function here. And if it decreases, meaning it gets closer to 0 fast enough, we can actually find the area of that curve. If we have a function that's continuous positive and decreasing, but it doesn't get small enough fast enough, then that area is going to end up going off to infinity. And we're going to look at some example problems where that happens, where we have integrals that converge or where we can find the area under the curve with limits that go off to infinity, and some where they can't, where we can't find the area because the area is going to be infinity. Here's the definition of improper integrals of the first type. These are going to be integrals where the bounds are going to be infinity, either positive infinity or negative infinity. And what we do, or how we evaluate these integrals, is that we rewrite that upper bound here, infinity, with a letter so that we do have a definite integral where we have definite bounds. And then we look at the limit as b goes to infinity after we integrate this. So to get around not having definite bounds here on our integral, we replace the infinity with a letter, and then we have a definite bound so that we can then use the fundamental theorem of calculus to evaluate this integral. Remember the fundamental theorem of calculus. It says that if you have a definite integral from a to b of some function of x dx, then if we find the antiderivative of f and plug in the upper bound minus the lower bound, we can evaluate this definite integral. The fundamental theorem of calculus only works when you have definite bounds. So how we get around that, whenever we have an infinity as a bound, we're going to replace that bound with a variable, and then we're going to look at the limit as that variable approaches infinity. That way we can use this fundamental theorem of calculus to evaluate our integrals like we always have. We're going to look at the limit as b goes to infinity if our upper bound is infinity, and typically we'll look at the limit as a goes to negative infinity if our lower bound goes to negative infinity. And if we have both bounds going to infinity and negative infinity, what we would do is we would pick some point in between negative infinity and infinity, typically 0 or some other nice number where the function is nice, and we would break this into two indefinite bounds. And then for this one, we could use form 2 that we had right here to evaluate the limit, and for this one we could use the first form to evaluate this integral. So if you have bounds going from negative infinity to infinity, you just break it into two indefinite integrals, and then you're going to use either 1 or 2 to evaluate. This will make more sense as we look at an example problem. So let's start with example 1. I don't know why I picked a problem with both infinities and 8s. Infinity's hard enough to draw without looking at an 8. Okay, so here we have the integral that goes from 8 to infinity of dx over x squared plus 64. First thing we do is we rewrite this as a limit as b approaches infinity of the integral from 8 to b of dx over x squared plus 64. So here's our integral. What technique can we use to evaluate this integrand? What does this look like? What type of problem? What if I rewrite the problem like this? Can you tell now what technique we should use to integrate this? In the denominator, we have a square root of x squared plus 64. These are mathematically equivalent because when you square a square root, they cancel each other out and you're left with what's on the left-hand side. So what technique should we use here? Trig substitution. And when we use trig substitution, what do? First thing we do is draw a triangle. So there's going to be my angle theta. There's my 90-degree angle. What is the hypotenuse going to be? The square root of x squared plus 64. What is the opposite side going to be? X, and the adjacent side, 8. Now I need to do my substitutions. What is x going to be equal to? Well, x over 8 is opposite over adjacent, and opposite over adjacent is tangent theta. So that means that x is going to be equal to 8 times tangent theta. When I take the derivative of x, I get dx, and that's going to be equal to 8 times secant squared theta d theta. And then the other piece that I need is the radical, and if I look at the radical over 8, that would be hypotenuse over adjacent, which means that the radical is going to be equal to hypotenuse over adjacent is secant, so that's going to be 8 times secant theta. What's the other thing we need to do when we change our variable of integration? We need to change the bounds. So the first thing I'm going to do is I'm going to plug in, let's use the lower bound. That's going to give me 8 over 8 equals tan theta. Well, that means that tangent of theta is equal to 1, so what is theta equal to? Tangent is equal to 1 when theta is equal to pi over 4. So my new lower bound is going to be equal to pi over 4. Now let's look at our upper bound. I have a b here, and if I put b over 8, isn't that just infinity over 8? So what is theta going to be? Pi over 2, isn't it? If you don't remember that, think about the graph of a tangent function. The tangent function looks like this, and when tangent's going off to positive infinity, that means that the angle is going to be pi over 2. If it was going off to negative infinity, the angle would be negative pi over 2. You've got to remember your trig graphs. And if you forget, just graph them in your calculator. Another way that you could think about this, if you didn't like that, is remember the little shortcut table that I gave you? So if you didn't want to look at the graph of the trig function, you could remember this table. Remember that tangent is equal to sine over cosine. So if we look at sine over cosine, at pi over 2, we're dividing by 0. 0 is where this is going to go off to infinity. So you have a couple of options here for that. The reason that I said that I didn't want to rewrite this integral right here until we had changed our bounds is when we change our bounds, we end up with definite integral. We don't have the infinity anymore because the infinity came into play whenever we were changing our bound. So that means that this problem is actually going to be the integral from pi over 4 to pi over 2. And then in place of dx, we're going to plug in 8 secant squared theta d theta. And then in place of the radical, we're going to plug in 8 secant theta. But remember that radical was squared, so we have to square both the 8 and the secant. And that's going to give us 64 secant squared theta. So now this problem that looked difficult to start with is actually pretty simple because 8 goes into 64 8 times. This secant square cancels with that secant square, and we're left with the integral from pi over 4 to pi over 2 of 1 over 8 d theta. And when we integrate that, that's going to give us theta over 8 evaluated from pi over 4 to pi over 2. So I'm going to pull that 1/8 out when I use the fundamental theorem of calculus, and then that's going to give me pi over 2 minus pi over 4. And getting a common denominator, that would give us 2 pi over 4 minus pi over 4. So that's going to be 1/8 times 2/4 minus 1/4 is 1/4. So this is just going to be pi over 4. And then we multiply numerator times numerator, denominator times denominator, and that's going to give us pi over 32. And that would be our final answer. In example 1, we only had one infinity, but when we go down to example 2, we see that we're going to have an integral that goes from negative infinity to infinity. And we said that when the integral goes from negative infinity to infinity, the first thing we need to do is break this into the sum of two different integrals. I'm not going to start with the integral, I'm going to start with the limit. I'm going to break this at 0 because 0 is typically a nice break point. So we're going to look at the limit as a approaches negative infinity of the integral from a to 0 of 2x dx over x squared plus 1 to the 9th, plus the limit as b approaches infinity of the integral from 0 to b of 2x dx over x squared plus 1 to the 9th. How would we evaluate these integrals? There's multiple ways to do this. One way to do it is a u substitution. It's not the way I did it on my notes before. On my notes before, I did a trig substitution. We can do this with a u substitution if you like. What would we let u be equal to? X squared plus 1. So then du is going to be equal to 2x dx. Well, we have a 2x dx right here for our du, so that's the 2x dx right here. Now the other thing I'm going to need to do is change my bounds, aren't I? When we do a u substitution, we've got to change your bounds. What is our lower bound going to be? Well, on the first integral, we get u equals x squared plus 1. And if we drop in an a right there, that's going to give us a squared plus 1. A is equal to negative infinity. What happens when you square a negative infinity? It turns into a positive infinity, and then we add 1 to that to infinity, and we still get infinity. And when we go to find our upper bound, we're going to plug in a 0 in place of x, and that's going to give us our upper bound of 1. This is for the first integral. For the second integral, since I'm using the same substitution, my lower bound is going to be 0 plus 1, and then my upper bound is going to be what? It's still going to be a positive infinity. So let's rewrite our integrals. This integral becomes the integral from infinity to 1 of du over u to the 9th. I'm just going to write that as u to the negative 9 du. Are y'all okay with that? Now because of that infinity, I want to look at the limit as b approaches infinity. And here I'm going to have the limit as b approaches infinity of the integral from 1 to infinity of u to the negative 9 du. When I integrate u to the negative 9, I'm going to add 1 to the exponent and then divide by the new exponent. So this becomes negative 1/8 u to the negative 8 evaluated from infinity to 1 plus the limit as b approaches infinity of negative 1/8 u to the negative 8, and this time from 1 to infinity. Are we okay with that? I'm going to rewrite my u to the negative 8. Since I have to evaluate this, I'm going to rewrite that with a positive exponent. So this is going to be the limit as b approaches infinity of, we're going to plug in our upper bound, and that's going to give us a negative 1 over 8 times 1 minus a negative, so that'll be plus 1 over 8b to the 8th, plus the limit as b approaches infinity. When we plug in our upper bound, we're going to get a negative 1 over 8b to the 8th plus 1 over 8 times 1. Now as b goes to infinity, we're dividing by infinity. Remember what happens when you divide by infinity? Think about the graph of y equals 1 over x. As x goes to infinity, if this was 1 over x, as x goes to infinity, y is going to what? It's going to 0, isn't it? So when we divide a function by infinity, we're going to end up with a 0. If the denominator gets really big, the value of that fraction gets really small. So this term is going to go to 0 when I evaluate my limit, and this term is going to go to 0 when I evaluate my limit. And so that's going to give us negative 1/8 plus 1/8, and that's going to be equal to 0. So the value of this integral from negative infinity to infinity is equal to 0. Let's look at a graph of that to see why that's the case. So looking at the graph of this function, I went ahead and typed the function into the calculator. I saw that it was going to be a really tight window, so I zoomed in on the window, and we end up with this graph. And we were looking at the integral from negative infinity to infinity. Well, out at infinity and negative infinity, we have a horizontal asymptote of 0, but we also notice some symmetry here. The area above the x-axis is equal to the area below the x-axis, and when that happens, we end up with a total area of 0, because the positive area will even out with the negative area, and it gives you a 0 sum there. The question was, if the upper bound and lower bound are both infinite, will the answer always be 0? And the answer is no. It's only going to be equal to 0 if you have this symmetry about the origin here. If you have an odd function that's symmetric about the origin, so that the positive area and the negative area are the same. It was because this was our function, and it was an odd function, that happened. Only when you integrate from negative infinity to infinity over an odd function is that integral going to be equal to 0. That was a good question. Thank you for asking. In example 3, we're asked to find the values of p for which each integral converges. P is a constant, so we're going to treat p as if it were a constant because that's what it is. What I mean by does the integral converge is that integral equal to a number? Is it equal to a limit? If it is, then we say that the integral converges. However, if that integral is equal to either positive or negative infinity, then we say the integral diverges. So we're asked to evaluate this integral and find the values of p for which this integral converges. In order to evaluate this integral, we're going to have to do a u substitution. So what are we going to let u be equal to here? Well, since I don't know how to integrate ln x, but I do know how to derive it, I'm going to let u be equal to the natural log of x. That means that du will be equal to dx over x. And notice we have a dx over x right here. When we do a u substitution, what's the other thing that we need to do? We need to change the bounds. So for our lower bound, we're going to plug in a 1 in place of x in our u. So that means that u is going to be equal to the natural log of 1. And what is the natural log of 1? That's equal to 0. For our upper bound, we're going to plug in a 2 in place of x, and that's going to give us the natural log of 2. That means that the integral in part A can be rewritten as the integral from 0 to the natural log of 2 of u to the negative p du. What I did was I moved this term up into the numerator, which caused the exponent to become negative. When we integrate this, that's going to give us 1 over 1 minus p, because we add 1 to this exponent, u raised to the 1 minus p, and then we evaluate this from 0 to the natural log of 2. Using the fundamental theorem of calculus, then we will plug in our bounds, and that's going to give us 1 over 1 minus p times the natural log of 2 raised to the 1 minus p minus 0 raised to the 1 minus p. 0 raised to any power is just 0. So what I'm looking at is the natural log of 2 raised to the 1 minus p. And I want to know the values where p is going to converge. Now, I've got to consider all of the numbers that go from negative infinity to infinity. There's one number that p cannot be equal to because we're not allowed to divide by 0. So that means that automatically p is not going to be equal to 1 because that would cause this term to be 0 in the denominator. So then the next thing I do is I look at the natural log of 2 raised to the 1 minus p. Well, here's the graph of the natural log of 2 when it's raised to a positive power and when it's raised to a negative power. The blue graph right here is when that exponent on the natural log of 2 is positive. That's going to converge because it's going to 0. When that exponent on the natural log of 2 is negative, this is going to go off to infinity. So what that tells us is that 1 minus p, in order for this to converge, has got to be equal to a positive number. So that has to be greater than 0. When I solve this inequality for p, I'm going to add p to both sides, and I get 1 is greater than p, which means that p has to be greater than 1 in order for this to converge on the bounds from 1 to 2. Another way of saying that 1 is greater than p is saying that p is less than 1. So if the bounds on this integral are between 1 and 2, this will converge as long as the power of p is less than 1. This is going to be the integral from 2 to infinity of dx over x times the natural log of x raised to a power of p. Once again, in order to evaluate this integral, I'm going to do a u substitution and let u be equal to the natural log of x, so du is going to be dx over x. I now need to change the bounds for this, but before I do that, I'm going to rewrite this as the limit as b goes to infinity, because we don't want infinities on our bounds on our integral. So I look at the limit as b goes to infinity of the integral from 2 to b of dx over x times the natural log of x raised to a power of p. I know what my u substitution is going to be. Now I need to know what my bounds are going to be. To get my lower bound, I'm going to plug in a 2 in place of x into my u substitution, and that's going to give me u is equal to the natural log of 2. To get my upper bound, I'm going to look at the limit as b goes to infinity of the natural log of b. Well, as b goes to infinity, think about the graph of a natural log function. The natural log function looks like this, and as that argument is going to infinity, what is the graph of y equals ln x approaching? As x's get bigger, the y's are getting bigger. They're going off to infinity as well. That means that I can rewrite this integral as the limit as b approaches infinity of the integral from the natural log 2 to b of u raised to the negative p du. And when we evaluate this integral, we're going to get the limit as b approaches infinity of 1 over 1 minus p times u raised to the 1 minus p evaluated from the natural log of 2 to b. And that's going to be the limit as b goes to infinity of 1 over 1 minus p times b raised to the 1 minus p minus the natural log of 2 raised to the 1 minus p. Notice on both of these, the exponents are the same. It's the bases that are different. Which one of these is going to dominate, the b or the natural log 2? And by dominate, I want you to go back in your mind to chapter 7.4 when we talked about rates of growth. Which one's going to get bigger faster? The b raised to the 1 minus p as b goes to infinity, or the natural log 2 raised to the 1 minus p? Remember, b is going off to infinity. Infinity is way larger than the natural log of 2, isn't it? So since the infinity is bigger than natural log 2, what that means is this function right here is going to dominate. I need to see what's going to make this function converge. So what's going to make an infinity raised to a power go to 0? What's going to happen? If infinity is raised to a positive power, I would end up with infinity raised to a positive power. And infinity raised to a positive power is going to get really big really fast. But what if that infinity is raised to a negative power? Infinity raised to a negative power becomes 1 over infinity raised to a power. And 1 over infinity raised to a power, that infinity is going to get really big really fast. And what happens to a fraction as the denominator gets really big really fast? It's going to go to 0, isn't it? So that means that in order for this to converge, this power has to be negative. So that means that for this integral in part b, first of all, p cannot be equal to 1, because if it is, that term goes to 0. And then the other thing that we need to have happen is this power on infinity needs to be negative. So 1 minus p has got to be less than 0. That's negative numbers. If we add p to both sides, that gives us 1 is less than p, or another way of saying that is that p is greater than 1. So if we have the integral that's going off to infinity here, this is going to converge for p's greater than 1. And that's going to come into play in chapter 10 when we start talking about p-series tests. So depending on the bounds on this integral, on part A, we converged if p is less than 1, and on part B, we converged when we're going off to infinity for p's greater than 1. So in chapter 10, when we start looking at infinite series, they're going off to infinity, we're going to say if we have something written in this form, that power on the term in the denominator has got to be bigger than 1 in order for the series to converge. That probably doesn't mean a whole lot to you right now. I'm just trying to forecast what's going to be coming up in chapter 10. And I want you to remember this discussion right now today when we get to that point in chapter 10. And I'll remind you of this conversation. In the first type of problems we were looking at, we had infinities as our bounds, either negative infinity or positive infinity, and those are called type 1 improper integrals. The type 2 improper integrals are what you get when you have a vertical asymptote. So the y's will be going off to infinity as opposed to the x's going off to infinity. So if our function is continuous on a semi-closed interval from a to b and is discontinuous at a, then we don't want to look at the integral from a to b. We want to look at the limit as some value approaches a from the right-hand side, because on this integral, we're approaching a from the right-hand side. So the limit is c approaches a from the right of the integral of c to b f of x dx. That's how we would rewrite our integral. If the function's continuous at a and discontinuous at b, then we would look at the limit as c approaches b from the left, because this interval, this range of values, is approaching b from the left-hand side. And if c is discontinuous at some point in the middle of your integral, say we have a vertical asymptote of a function between a and b, then we would rewrite that as the integral from a to c plus c to b. We would have a break where that vertical asymptote is, and this we would look at the integral as we approach c from the left, and here we would approach c from the right. It's just a combination of these first two things. That's what this is. So in each case, if the limit is finite, we say that the improper integral converges, meaning that the limit is equal to some number. But if the limit goes off to infinity, we say the limit doesn't exist and the integral diverges. In example 4, we're asked to evaluate the improper integral or show that it diverges. This is going to have a vertical asymptote at x equals 4, because that's where the denominator of this function is equal to 0. So what I want to look at the limit as c approaches 4 from the left or from the right? Well, let's look at this again because I don't think I made myself clear. Let's say that this is our vertical asymptote right here, and I want to look at the limit then as x goes to a. So this would be continuous on the integral from a to b like this. So when I look at what c is going to approach, if the vertical asymptote is where a is, then I would look at the limit as c approaches a from the right-hand side because we're coming up on a from the right-hand side. If I had a vertical asymptote at b, there I would want to come up on b from the right-hand side. I would want to look at the limit as c approaches b from the left-hand side because I'm approaching b from the left, not from the right. So this would be like this. Looking at our problem, we have a vertical asymptote at 4. So this is not going to be defined at 4, but it is defined at 5. I want to approach 4 from the left or from the right? That's from the right, so I would look at the limit as c approaches 4 from the right-hand side. Sometimes it helps to draw a picture. So this is going to be the limit as c approaches 4 from the right-hand side of the integral from c to 5 dx over x minus 4 to the 1/2 power. How would I evaluate this integral? Well, that 1/2 power is the square root. I could do a u substitution. So what would I let u be equal to here? I'd let it be x minus 4. What is du equal to? It's equal to dx. Well, great, I got a dx. So this is going to be u. What do I have to do whenever I change my variable of integration? I have to change the bounds. Looking at the lower bound, we're going to have the limit as c approaches 4 from the right-hand side of c minus 4. Well, as we're getting closer and closer to 4 from the right-hand side, what is this going to be equal to? It's going to be 0. For our upper bound, I get u equals 5 minus 4, and that's going to be equal to 1. So when I rewrite my integral, this is going to be the limit as c approaches 0 from the right-hand side, the integral from c to 1. This is in the denominator with a positive exponent, so I'm going to move that to the numerator with a negative exponent du. What do I get when I integrate u to the negative 1/2? I'm going to add 1 to the exponent. That makes it a positive 1/2. And when you divide by 1/2, you get 2. And then that's going to be u to the 1/2, which is just the square root of u, evaluated from c to 1. So when we apply the fundamental theorem of calculus and plug in our bounds, I get the limit as c approaches 0 from the right-hand side of 2 times the square root of 1 minus the square root of c. The square root of 1 is 1, so this is just going to be 2 minus, and what do I get as I approach 0 from the right? It's positive value, so the square root is defined, but what is the square root of 0? It's 0, and 2 times 0 is 0, so this would be 2 minus 0, which is 2. Because this is a finite number and not an infinity or a negative infinity, we would say that this integral converges to 2. Okay, the question was, do we have to plug in what u was equal to back here? And the answer is no, because we changed our bounds. If we didn't change our bounds, then yes, we would have to go back to the original variable, but we would use the original bounds then. Because we changed the bounds, it saves us the step of having to go back to the original variable. That's why I like changing the bounds when we do these. You don't have to look back to the original variable. The only time you have to go back to the original variable is if you have an indefinite integral and you have no bounds to change. Very good question. Thank you. The question was, how did I get 2 square root of u here? Let me walk us through the steps. So when I integrate this, that's going to give me u raised to the negative 1/2 plus 1, and then I divide that by negative 1/2 plus 1, but do the arithmetic. 1 minus 1/2 is 1/2, and when you divide by 1/2, you're going to flip and multiply. So that 1/2 became the 2, and u to the 1/2 is the square root of u. Just use your power rule. If you're struggling with that, then write out the steps. If you can't just see the answer in your head, write this out. I would consider this scratch work, but if you need to write it out, write it out. I would rather you show more work than necessary than less work than necessary, or even risk getting the problem wrong by not showing enough steps. Theorem 2 is something that we're going to use in Chapter 10 quite a bit as well. It's something called the direct comparison test. This says if f and g are continuous on an integral from a to infinity where f of x is going to be positive and it's less than g of x, less than or equal to g of x for all x's that are greater than or equal to some number, then the integral from a to infinity of f of x dx converges if the bigger function converges. And the integral of g of x diverges if the smaller function diverges. So I think using bigger and smaller is the easiest way of doing this. Let me kind of draw a picture to explain what's going on. What this says is that f of x is going to be less than or equal to g of x over some interval from a to infinity. So notice these two graphs. Even though over here g of x is less than f of x, once I get to this point a, f is always going to be less than or equal to g everywhere from a to infinity. Now, what causes an integral to converge or diverge? It converges if that integral is equal to a number, and it diverges if it's equal to infinity. If you think of convergence as being that integral is equal to some number, meaning it doesn't go off to infinity, the way that you can think of this is the smaller function is going to converge if the bigger function converges. So if the bigger function converges, meaning it's not equal to infinity, then the smaller function's not going to be infinity either. Because I've got the bigger one, which should be closer to infinity, than the smaller one, because we're looking at the area under the curve. If the bigger one's not equal to infinity, the smaller one's not, so that means that the smaller one will converge as well. This one says that the bigger one's going to diverge if the smaller one diverges. What causes an integral to diverge? It's that that integral is equal to infinity. It's not going to be negative infinity because we have this condition that the functions are going to be positive. Integrals, remember, are area under the curve. So if this smaller function has an area of infinity, guess what? The bigger one does too. What we would say is this. If the smaller function diverges, then so does the bigger one. Because if the area under this curve is going to be infinity, the area of the bigger function is also going to be infinity. This is called the direct comparison test, where we have to know something about the convergence of one or the other functions before we can use it. This is also going to be a test that we use in Chapter 10 to check convergence of series, infinite series. Theorem 3 is the limit comparison test. This says that if the positive functions f and g are continuous on an interval from a to infinity, and if the limit as x goes to infinity of the ratio of these two functions is equal to a finite number, a positive finite number, then both of the integrals either converge or diverge. This means that they do the same thing. If the limit as x goes to infinity of the ratio of both integrands is equal to a positive finite number, then both integrals are going to do the same thing, meaning they're both going to converge or they're both going to diverge. That's called the limit comparison test. Example 5. Use integration, the direct comparison test, or the limit comparison test to test the following integral for convergence. If more than one method applies, use whatever method you prefer. I typically say let's use what first comes to mind to use. So to evaluate this integral from 9 to infinity, we have the integral of 1 over the square root of v minus 1 dv. Could we evaluate this? Well, the first thing I want to do is rewrite this as the limit as b approaches infinity of the integral from 9 to b of 1 over the square root of v minus 1 dv. Can we integrate this? Use a u substitution. Yes, we can integrate this if we use a u substitution. What am I going to let u be equal to? V minus 1. So what is du equal to? dv. When we change our variable of integration, what else do we also have to change? We're going to change the bounds. So for our lower bound, we're going to look at u equals 9 minus 1, and 9 minus 1 is 8. So our new lower bound is going to be 8. Our new upper bound is going to be the limit as b approaches infinity of u equals b minus 1. Well, as b goes to infinity, this becomes infinity minus 1. And what do you get when you take away 1 from infinity? Infinity. Let's rewrite this. This is going to be the limit as b approaches infinity of the integral from 8 to b of, this is now going to be u raised to the negative 1/2, because the square root is a power of 1/2. It was positive in the denominator. When I move it to the numerator, it's going to be negative dv. When we integrate this, we're going to get the limit as b approaches infinity, add 1 to the exponent, divide by the new exponent. That's going to give us 2 square roots of u, just like the last problem that we did. The bounds go from 8 to b. So this is going to be the limit as b approaches infinity of 2 times the square root of b minus the square root of 8. Well, what happens as b goes to infinity of this term? The square root of infinity is infinity. And infinity minus a constant is still infinity. This integral is equal to infinity, so it diverges. Anytime your integral is equal to either positive infinity or negative infinity, we say the integral diverges. Do y'all know what these 3 dots mean? We stole that from the English department. That they mean therefore. This is English shorthand. We're going to be using it a lot in Chapter 10, so get used to it. Example 6. Perform a test to determine if this integral converges or diverges. If this would have been an x squared instead of an x cubed, I would have said, let's integrate this using trig substitution. But because it's an x cubed, I can't do trig substitution on it. So do we have a test that we could do that would be easy to check this? And the answer is yes, we do. Remember the limit comparison test? All I got to do is look at the ratio of 2 functions and see if it's equal to a number. So I want to use the limit comparison test on this problem. And what I want to compare this to is the integral from 2 to infinity of 1 over x to the third dx. How I got this integrand was I looked at this integrand and I saw the only difference here is this constant. Because this is easy to integrate. I can integrate this and tell what it does. Agreed? So since I'm going to compare it to this, I probably want to know what this integral does. So I'm going to start by checking the convergence of the integral from 2 to infinity of 1 over x cubed. Because when I use the limit comparison test, both integrals end up doing the same thing. So I need to know in advance what this integral is going to do. So I'm going to rewrite this integral as the limit as b approaches infinity of the integral from 2 to b of x to the negative 3 by moving that term up into the numerator dx. When I add 1 to the exponent, that's going to give me x to the negative 2. And divide by negative 2 gives me a negative 1/2 out front. And this is going to be the limit as b approaches infinity of this from 2 to b. So when I plug in my bounds, that's going to give me the limit as b approaches infinity of negative 1/2 times. Now that x to the negative 2 I could write as 1 over x squared. So that's going to be 1 over b squared minus 1 over 2 squared. And as b approaches infinity, what happens to this term? 1 divided by infinity is what? It's 0. So this limit is equal to negative 1/2 times negative 1/2 is positive 1/4. Therefore, this integral will converge. Sorry, this was negative 1/2 times negative 1/4 is going to be positive 1/8, not 1/4. So since the b goes to infinity, this ends up being negative 1/2 times negative 1/4, and that's going to give us a positive 1/8. That is a positive finite number, therefore this integral converges. So now I need to use the limit comparison test to see if this integral converges. The question was, why did I choose this particular thing to compare to? And the answer is because it is a simple function that I already knew in advance would converge based on the work that we did in example 3. Remember in example 3 we said that if we have a power that's bigger than 1 in example 3b, then that's going to converge. And this is the same as our integrand over here without the constant. And that set me up to use the limit comparison test. In the limit comparison test, what you want to compare to is something so that you have the same basic integral, but you strip away the constants. Let's just look at the limit comparison test. The limit comparison test says we look at the limit as x goes to infinity of the ratio of 2 integrands. It doesn't matter which one goes on top or which one goes on bottom. So I'm going to look at the limit as x approaches infinity of, I'll put my problem on top, that's 1 over x cubed plus 3 divided by, and then what I compared it to, 1 over x cubed. When you have a fraction over a fraction, you want to rewrite that complex fraction. So we're going to flip the fraction on bottom and multiply by the one on top. And that's going to give us x cubed over x cubed plus 3. Now, do you remember from calculus how to evaluate these limits? So x cubed divided by x cubed plus 3 as x goes to infinity. We can either use L'Hopital's rule, or we can look at this and say, well, the degree of the numerator is the same as the degree of the denominator, so this limit is going to be equal to the leading coefficient of the top over the leading coefficient of the bottom. Or you could divide every term by x cubed. You have several options available to you, but you do need to remember how to evaluate limits. So this is equal to a positive finite number. So according to the limit comparison test, that means that both functions are going to do the same thing. Since what we compared this to converges, that means that our integral converges as well. And we would say that it converges by the limit comparison test when we compared it to this convergent integral. On a test, you can't just look at this and say converges by the limit comparison test. You've got to show all these steps. You've got to tell me what you're comparing to. Show me that what you're comparing to either converges or diverges, and then look at the limit of the ratio of those two integrands to see if that's equal to a finite number. If it is, then both integrals are going to do the same thing. But all of this work has to be here for this problem. Okay, the question was, so this is just checking our work. So if one converges, the other converges. That statement is true only if this limit is equal to a finite number. The test is inconclusive if this limit is equal to infinity. Let's look back at the limit comparison test. It says if. If means these conditions have to happen. If the positive functions f and g are continuous, and if that limit is equal to a finite number. Then we get this. They do the same thing. If that limit is equal to anything other than a finite number, this test would be inconclusive and you would have to try something else. We can't just say this test fails if we get an infinity. There's two things that have to happen. Okay, first of all, you have to have continuous positive functions, and then the limit of the ratio of those two functions has to be equal to a positive finite numbers. If both of those things happen, then we would say that both of the integrals converge, or both of the integrals diverged. I didn't force a fit here. I'm past that, past trying to force a fit for something. I let happen whatever's going to happen. How I decide what I want to compare to is I take the constants out of this. If this would have been a 2 in front of this 2x cubed plus 3, I still would have compared to 1 over x cubed. That's the most basic function similar to this function. That 2 wasn't there, but that's how you decide what to compare it to. It's a good problem. All right, this is going to wrap up section 8.8.